So continuing our discussion with linked lists, let us see linked list operation. Now there are various operations that can be applied on linked list, and we'll be talking about abstract data types later on, and we will try to formalize what we are talking today. But as we are sticking today to linked list, we won't be able to do three main operations. First is to add elements to our list, then to remove them, and traverse the entire list. These are the basic operations which can be done on data structures, but in linked list also these three are very important. Now, how to implement those? First is traversal. How traversal can be done? In arrays, what happened? In arrays, it was fixed, contiguous. So linked lists do not supply functionality to directly access the ith element. In array, order 1 complexity was there. We'll talk about this all complexity later on. But because in array, you just have to go to that particular value, the ith value, and you can access it. But linked list does not provide you with this facility. So what we do is we start with the first node, and then we go to the next node, and then repeatedly we traverse through each node. For that, we declare a variable called this item p, means this will be a pointer p of type item, means pointer to that structure, that will keep track of the current node which we are looking at. So this p will start, or p starts out as a pointer to the head element. First it will be head element, then with each operation, if we apply a for loop, we update this to the next pointer. How this is done? The code will be like this: traverse. This will be item, means item. You have already known that we have created a structure earlier in the earlier discussion. We have created a structure, so that structure type first will be our pointer to this structure. And what we will do is from head, because head is the starting point, and till null, means the first one to the last one. You know that the first one will be pointed by head, and the last one will be pointing to the null. So from head till null, we traverse it. Maybe p is equal to p this arrow next. So we do something, say some print value or something, and we can also traverse recursively, because we have learned recursion. What we can do is void traverse, same function, item head, but we have to do like this: traverse head next. So this function can be called like this, right? Traverse head next. This is the actual line which is written here. This is the line. So the good thing about recursive implementation, as it is simple also, that it is very easy to make it traverse the list in reverse order, even if the list is singly linked. So with recursion, you can easily traverse in the reverse order, and you can simply change the order of the true statement, that is calling traverse before doing and processing, and the processing, that is printing, etc. But we'll be seeing it more. But the task of printing in a linked list in reverse order is quite popular. Interview question: why? Because it tests knowledge of linked list and recursion. So most of the time, reversing or asking how to reverse or how to traverse a linked list in a reverse order is a very much asked question. Then, as we are done with this traversing, let us talk about addition. We want to add a value or add a node to our linked list. So we take our input data item and create a new item from it. So this element will usually be added to the end of the list. So it will probably be pointing to the next pointer will be to the null, because it will be kept in the rear point of a linked list. We can also add it in the beginning of the list, so which could change somewhat implementation. But in order to add it at the end of the list, we just need to find the last element which is called the tail, and then simply set the next pointer of this last node to our new element. Okay, so we need a special case for previously empty list, because it may happen the list does not contain anything, the list is empty. So we have to set the head pointer which was previously null. So this is how the code will look like to add a new element in our linked list. Please notice this is a special statement, or you can say expression. So we want to add item which is of type head, and this is the value. So item, new element we have created through our a kind of constructor thing which we introduced while making the structure of a node. And we just check here that if head is null, means there is no, not at all, or not even a single node in your linked list. So what we'll do is head is equal to a new element. Otherwise, the simplest thing is this item P will be head, and the next will be, we will travel it to null, means we have to go to from first to last node. So this is how we go to the last node, and simply the last node will be P, next will be P, and the new element will be assigned to P next. So this is so simple as far as adding is concerned. But we need to see this strange construction of item head. Since we want to pass the head of the list, which is an item star. The item star means this is a item star type, but we may also need to change it when it was null. So what we did was we need to pass a pointer by a reference. That is why this strange construction. And there can be a shorter implementation also using recursion. We want to add, you have already known about this, and we want to place this n value. So if head is not equal to null, if head is not equal to null, what we'll do is head will be equal to new item n equal to null, and else add, just we call recursion head, else add head next, and the value will be n. So we notice that both the recursive and the iterative implementation have to travel the entire list to find the last element. This is inevitable, because in an array it may be possible to access or to go to a specified location, but in linked list you have to already start, or always start from the first node and then go to the last node, and this can be rather ineffective. That is why it is always a good idea to not only maintain a head pointer but also have a tail pointer. That is why we have discussed in the earlier discussion that we keep this tail pointer also to point to the last element. Why? Because we don't want to traverse the entire list every time we want to add something. Then coming to our removal, if we are giving a pointer item to remove, we have just added, we have seen how to add. Now we want to remove a particular item to an element of a list we would like to remove. We will eventually have the command delete to remove. But before that, we also need to make sure that the link structure of the list stays intact. Means even while removing, you have to see that it should, or after this removal, the list should be a linked list. This is what we need to see. So we need a pointer previous to the element right before to remove in the list, so that we may set this previous next to remove next. Means if this is a node and this is a node, okay, there are three nodes. If I want to delete it, now this node has next pointed to this element. If I am trying to delete it, the previous node, which is the previous node, the next of this previous should not point to this. Now the next of this previous should point to the removal of next. Means this we have removed. So now this remove next will be actually the previous next. This is the line which is showing that, because this will be removed. So one way to get this pointer is to start from the beginning of the list, as we know that this has to be there, and we scan through until we find the node P, and then we do our verb. P next will be equal to remove. But that will take a long time, somewhat tedious. So better solution is to store each element or each item, not only a pointer to the next element to the list, but also the previous element. Means what I'm saying is, previously in a node, what we have a value and we had a pointer to the next. What we are suggesting is, let us have one more node. In this one more node, one more value. The value, this will be pointing to the next, and this will be pointing to the previous, and this will have this first partition, second partition will have a node, third partition will be to the next. So in this way we will be having a idea or a solution to keep track of the previous value also and next value also. And this idea is known as doubly linked list. This is known as doubly linked list, and unless you have a strong reason to prefer a singly linked list, try making doubly linked list only. So we have already seen our definition. What we are going to add here is item previous. Why this item previous? Because we are dealing with now a doubly linked list which also have a previous pointer or a pointer which is pointing to the previous node. So in this function, for adding a value, we set this new empty previous to null because we didn't have in the first case, and next element to previous to p, which is in the second case. Now to remove an element, we can now write remove. This you already know why we had done this. An item to remove, because we need a pointer to remove an element also. So this I already suggested, because to remove it, if this next has to be pointed to the next, if this is deleted, it has to be pointed to this next. So to remove next will be to remove previous next, and this to remove previous will be to remove next previous, and we just delete this to remove. This item is easily deleted. So this sets the next pointer of the preceding element to the next pointer of the element which is to be deleted, effectively unlinking it. So actually we are not deleting it, we are actually unlinking it. We are just playing with the pointers. And this is the lines for the previous pointer. So while this looks good at the first sight, we have to be very cautious when this element we want to remove is the head or tail. If you want to remove the mid one, it is okay, but for this head and tail you have to be very cautious. So to remove this, to remove previous or to remove next, this could be null, which means we can't change their pointers. But in those cases also we need to put, or we need to update the corresponding pointers. So this will be the actual implementation. You want to remove head, and to remove will be there. So we need to just check that if this is head, this implementation will be there, and if it is not equal to null, this implementation will be there. So the real reason for having this doubly linked list is why? Because they make deletions much easier and cleaner, right? And a side benefit of this doubly linked list, which can be easily traversed back to front. This is also we started talking when we discussed linked list, and now we have reached to a point where we can easily traverse it from back to front also. Sometimes that this listed as a reason for having doubly linked list, but what we think is that a red herring, because we generally want this to be doubly linked, but one line is always there that it depends actually on your work, what functionality you want, right? So hope you saw this version of doubly linked list. Now we have recursive definition also of linked list. What is recursive definition means? A linked list is based on our discussion. We actually have not defined it just now. We haven't yet said exactly how to distinguish a linked list from a not linked list, right? There has to be something which makes this linked list different from others. What we can say is, it is a bunch of items where each item has associated data and pointers to another item. but one of the items doesn't point to anything. That is the last item. And second, this would include a lot of nodes, all of which points to one another node. But in this discussion, what we can try is a bunch of items, each of which points to one another node and is pointed to by one another node, except for one node that points to no other node, and this one node which is not pointed to by any other node. So maybe this definition might be confusing to you, but this would be correct, but quite difficult to understand. So let us make it very short. We can draw a recursive definition, which we have already seen, and we try to define this linked list. First is a linked list. The first is the empty list is a linked list, and second is the node that points to a shorter linked list is a linked list, right? We need an adjective is shorter. Why? To exclude a one node list where the node points to itself, which would be the case. It would be pointing to a linked list of the similar length. Okay. So this is the recursive definition of our linked list, but don't worry about this if you don't understand. We'll be talking about this a lot. So till then, take care.